We will wait. There are still some gaps. People may be coming in.
I have a couple of announcements before the session. One is regarding the poster. So those who have posters can display, say, tomorrow. Tomorrow is supposed to be the poster session. And I request all the participants to visit the posters post-lunch. That is one thing. Second is regarding the lab session. So, I mean, the hands-on session tomorrow. That will be conducted in 2 sessions. The first session will be led by Professor Varahan. He'll be giving tutorials. After that, we'll have data analysis using Python, correct? Which will be led by Pavani. That's all. You can.
So, tomorrow afternoon is the oral exam for me. You are going to ask questions. Are you with me? Every class is an oral exam for me, right? That's right. I have to answer all the questions. In particular, tomorrow afternoon, the questions you wanted to ask, if you have not had a chance to ask, you always have a chance to ask, but you didn't happen to ask, please bring it on. With me? We'll work some problems. I would like to start with your questions. And with me? We'll spend about an hour. About an hour tomorrow morning? Tomorrow afternoon?
Tomorrow afternoon, 1 hour.
1 hour. 1 hour we will do the hands-on will be, the first part will be hands-on with me.
It is actually 2:30 to 3:30 first session, and second session is from 3:30 to 4:30.
And my friend wanted a copy of the slides. So
all the slides by today itself.
Good. One good source is NPTEL. NPTEL, I have 40 sets of lectures, which is what a 3-credit 1-semester course. Understand me? So if you follow through the NPTEL course, that will provide you a guideline. And I'm going to give you copies of all the NPTEL slides with Dr. Govind. And I'm also going to give my appendix, because my friend asked me the question, where do I read about vector space? I forgot to tell that my book consists of 32 chapters. The appendix, there are A to G, vector spaces, matrices, multivariate calculus, optimization theory, sensitivity analysis, Fourier transforms. So there are 6 appendices, and the book is already 700 pages long. So the Cambridge University Press says, why don't we just put it aside? So whomever buys the book will get a copy of the appendix free. So the book is expensive. I know you have to pay in dollars. So what is the best way to get a book? Please go back to your parent institution, ask your library to buy. All of you? INCOIS has, NCMRW, they have a couple of copies, and likewise. So whichever is your parent institution, your library will respond if researchers say, I want to have these books in our library. So please take action so you can have the library. So what I'm going to give you is, I'm going to give you a copy of all the slides and all the appendices free through Dr. Govind. You can talk to him, he will make it available so that you all can download it. That works? Good. All of you? Good. And I also want to tell you that, welcome. Class, please say hello to my friend, Dr. Amit. He is a member of the faculty here, and also he is the head of the data science program at ICER Pune. Last time, ICTS conducted the same workshop some 5 years ago, 7 years ago. Oh gosh, okay. He was the coordinator. He also works in data assimilation. He's a physicist by training. And
he's also giving a couple of lectures for this week.
He is. Oh, I was planning to come there. He's going to give talks on Thursdays and Fridays. Welcome, sir.
Thursday and Friday, not Thursdays and Fridays. Not next week.
Oh, okay. Thursday and Friday, not Thursdays and Fridays. That's right. Thursday and Friday. Thursday, 1 talk. Friday, 2 talks. Yeah, that's right. I'm glad you are here.
I was just worried that maybe you're introducing so that I give the talk now. It sounded like an introduction like that.
No, I introduced Maithili when she joined us last class. I want them to know that my good friend is here. Good. So, this afternoon we are going to talk about the underdetermined static deterministic problem. Are you with me? So I'm going to start with the same equation, z is equal to h of x. I have the model space. I have the observation space. O is Rm. Model space is Rn. I have x. I have z. That's a bridge. The bridge is h. That helps to bring the information from the observation space into the model space. And x is the unknown. I know h. I know z. I need to find x. Now I would like to, before I talk about this problem, and what is the problem we want to talk about? This is m. This is m by n. This is n. We are going to be specifically interested when m is less than n. Underdetermined problem. But before I go there, I want to introduce you to terminology of what's called an inverse problem. The problem we have been talking about belongs to the class of inverse problems. If there is an inverse problem, there must be a direct problem. So what is a direct problem? What is an inverse problem? And what is the relation between this problem to direct and inverse problems? So I would like to be able to get that out of the way. Suppose there is a black box. It is an input. And there is an output. And the black box, let us assume, is F. F transforms the input and output. So let's call the input as X. Let's call the output as Y. So what are the general class of problems we can do? One is called the direct problem. Another is called the inverse problem. And what is the direct problem? X, F are known. Compute Y. The input and the transformation are known. Computing the output, the flow is this way. That's called the direct problem. So what are the examples of direct problem? Given a differential equation and the initial condition, solving the solution for the equation. With me? What is the inverse problem? The inverse problem can be of two types. Input given, output given, I want to find F. Input, output known, find F. The problem that we did in the morning What is that? Y is a straight line. Mx plus c. Understand? I don't know M and C. So knowing the parameters is equivalent to fixing or estimating the function. So knowing x and y, knowing the input-output x and y, finding f. Another way would be, another way inverse problem can occur is that I know f, I know y, find x. Are you with me? X-ray, CAT scan. You know what the CAT scan properties are. You are the object. You get the image. Are you with me? So you know the thing that transforms. You know the output. I want to know what is inside. Are you with me? So every medical diagnosis problem, from the symptoms to the cause. From cause to symptom is what they learn while they are in college. That is what makes them doctors. Then they come to the area, what do? They find the symptoms and look at the cause. So every medical diagnosis problem is an inverse problem. But while in college, they learn the direct problem, how to relate certain deficiencies in anatomy and how will it exhibit itself outside. The causes for various diseases is what they study. In practice, they see a disease, they want to be able to classify and cure. Are you with me, please? So every medical diagnosis is an inverse problem. What are other examples of inverse problem? A plane crashes. It's rare, but it does happen. So plane has been working all right, but suddenly it crashes. Then engineers come and comb the area. They collect all the debris. They try to reconstruct the plane and to find out which part of the plane did not function well. What are the shears in the metal? So based on the properties of the broken parts and trying to rebuild the plane, they try to identify, oh gosh, this is because of this it went bad. Because of this it may have gone bad. And it takes time. So the report may come 1 year later, but when the report comes, the manufacturing people get a feedback. Because of this it may have. For example, there was a flight from Brazil to France. The plane kept climbing up and up. Before a certain level, it can't go up. It went down 6,000 feet into the Atlantic. And when they dug up and things and found out what did they find, the pitot tubes that measure the height was malfunctioning. Are you with me? A simple things. So we learn from every crash what may have led to the crash, the cause. So cause and effect, going from cause to effect is forward, from effect to the cause is inverse. So in solving problems of this kind, if you give me h and x, if I give you h and x, I can multiply a matrix vector to get z. That's a forward problem. Here I know h, I know z, I want to find x. This is an inverse problem. So almost all of the problems of interest in data assimilation are inverse problems. I want to be able to estimate the initial condition. I want to be able to estimate the parameters. We are not the only one doing inverse problems. We are in good company, doctors. I'll give another couple of examples to be able to visualize. Detective. A bank has been robbed. Detectives come. They do clear examination of the place. From there, they have to guess who may have caused this. What gang are capable of being able to impart this kind of damage? Every detective work is an inverse problem. So the police department people, the doctor's office, they do something very similar to what we do in dynamic data assimilation. But they don't talk about models the way that we talk about models, but they have the model here. The doctor has the whole anatomy book in his understanding. All of it in place. So direct problem, inverse problem, estimation problem, And we are talking about a class of static inverse problem. 4D war becomes a dynamic inverse problem. Different ways of looking at the same thing. Good. So with that out of the way, we found in the last lecture, when m is less than n, it is underdetermined, it has infinitely many solutions. In this case, E is equal to Z minus H of X is always 0. There are millions of X for which this can be satisfied. If there are millions of X for which this can be satisfied, the cost function J of X, which is E transpose E, is identically 0 for all X. So I'm dead on arrival. So the old path that we walked is a good path for solving problems when m is greater than n, but that's of no use to us here. All of it, me? So why is that? There are infinitely many X for which Z is equal to H of X. So how do I reformulate the problem? Among all the X's that satisfy the constraint Z is equal to H of X, I want to find one with minimum energy, where the energy of a vector is measured by the Euclidean norm. Are you all with me, please? Square of the Euclidean norm. Why square of the Euclidean norm can be thought of as a generalized form of energy? In physics, kinetic energy is 1/2 of mv squared. So kinetic energy is proportional to the square of the velocity. So in mathematics, we can think of square of a particular quantity could be a quadratic term, could be a representation of the energy. So one way we are going to measure the energy is by the square of the Euclidean norm. Square of the Euclidean norm means what? Sum of the squares of the components of the vector. Are you with me? And I want to minimize that. So our goal is similar. Except that, in the old case, there was no solution that satisfies Z is equal to H of X. Here there are millions of X for which Z is equal to H of X is true. So among all the solutions, I want to find the one with the minimum norm. You may ask a question, why minimum norm? Well, I need to be able to get a handle on this particular problem. So I'm going to illustrate the method of solution through assuming my goal is to find the one with the minimum norm. If you are not satisfied, give me your goal. I can replicate the same method on your goal. All of it, me? So I'm going to reformulate the problem like this. Minimize the square of the norm when Z is equal to H of X. That means among all the solutions of this linear equation, I want to find the one that is the minimum energy. So this is called the constraint. This is called the objective function. So this problem is a constraint minimization problem. So minimization problem, unconstrained and constrained. What is an example of an unconstrained problem? The one that we did in the morning. Are you all with me? What was this? This is the sum of the squared errors. Where E of X was equal to Z minus H of X. Here, I want to find X wherever it may lie on the n-dimensional space. There's no constraint. So this is an unconstrained minimization problem. This is a constrained minimization problem. If there's no constraint, what is the minimum value of the square of the norm of X? 0. When does it happen? At the origin. So as an unconstrained problem, it doesn't have any teeth. It doesn't have any teeth. It's a constraint problem. Every one of you must have solved a constraint optimization problem in your first course in calculus. What is the problem? Suppose I am given a wire of length L. I want to be able to find a rectangle. What is the maximum area of the rectangle whose perimeter is fixed to be L? Do you remember the problem, please? You cannot have passed your BSc physics or mathematics without solving that problem. Every calculus book in the world has this problem. I know in India, every book has that. Why? I grew up in India. I know the Indian textbooks. All of you? How many of you remember that? Where did the rest of you go to school? Come on, guys. In India, you can get a or 90% without doing certain topics, right? Come on, maybe you neglected that. But if you go back to your book, this problem is a very typical problem. What is the constraint? My wire is fixed length. I want to be able to enclose an area. I'm going to constrain the area to be a polygon. With me? So let's solve the problem before we come in here. So this is L, this is B. 2 times 2L plus 2B is equal to L. L is fixed. I want to find the area, which is LB. Maximize LB when L plus B equal to L by 2. All of it with me? Homework problem for you. You got to do this tonight. How do you do that? I'll give you a quick example, a quick idea. You eliminate B. So kick B to the other side, L as a function of B, substitute here, you will get a quadratic function. Are you with me? You will get a quadratic function of L, first derivative, second derivative, first derivative must be 0, second derivative must be negative. What is the answer you should get? L must be equal to B. Are you with me? That I want you to verify. So what is this method? This method is called method of elimination. This problem is a variable in 2 problem, but the constraint enables you to express one variable in terms of the other variable. So you convert a 2 variable problem into a 1 variable problem by eliminating one of the variables using the constraint. You reduce the dimensionality of the problem by using the constraint and solve the resulting lower dimensional problem by applying the basic principles from univariate calculus, namely at the maximum, the first derivative must be 0, second derivative must be negative. Homework problem, please verify. I have already given you the method and the solution. Are you with me? But this method is good only for simple problems such as this to get a feel for it. But in here, this is an n-dimensional vector, this is a m-dimensional vector, this is the matrix. So if I want to be, can I in principle use the method of elimination? I can, but I had to pull my hair. Are you with me? It's not easy. In principle, I can do. So what am I looking for? I'm looking for an alternate method. That method is called method of Lagrangian multiplier. How old is Lagrange? As old as mathematics. Gauss, Lagrange, Newton, Leibniz, these are some of the founders of modern calculus. So the Lagrangian method is called Lagrangian method of undetermined multipliers or Lagrangian multiplier. So what did Lagrange do? He expanded the problem by introducing a new set of variables. He converted the constrained problem into an unconstrained problem in a larger dimensional space. So he embedded this constrained problem as an unconstrained problem in a larger dimensional space, and he showed that this unconstrained problem, when solved, gives you the solution for the constrained problem. Unconstrained problem we know how to solve. How do we solve? Gradient is 0, the Hessian must be symmetric and positive definite. That's a well-established trail of arguments. All of it me? Now, do you see the formulation is different? The methods are different? Constrained, unconstrained? That's why. So, there are two methods for solving unconstrained problem. Constrained problem. One is by method of elimination. Another is method of expansion. Lagrangian multiplier technique. Lagrangian method. I'm now going to illustrate the use of Lagrangian multiplier technique as far as the elimination is concerned. This is a homework problem. Please do. Please do. Okay. Now, having done this, I want to talk about the Lagrangian method. I'm not going to derive the Lagrangian method. I'm not going to prove the Lagrangian technique. But I'm going to show why it works, how it works. I'm going to show how it works, why it works, how Lagrange argued. That's a deeper question in optimization theory. But that is something I would like you to go back and read. Are you with me? That should be a motivation. I want to know. I know it works. I want to know why it works. All of you? Good. So how does the Lagrangian multiplier technique work? So originally, I have this variable x. I'm going to build a function x lambda. Here, x is Rn. Lambda is going to be Rm. Lambda is called the Lagrangian multiplier. X is the original problem variable. I'm going to construct the Lagrangian. This is called the Lagrangian. And what is that? That is equal to x squared. I'm going to, well, I'll put it later down. Now, how do I build the constraint into that? Z minus h of x is the constraint. Please remember, this is a M vector. In optimization problem, I only know how to optimize a scalar valued function of a vector. If I want to optimize multiple components of the vector, that becomes multi-objective function. You remember that? We talked about it in the morning. So I have to convert my problem. I have to remain within the realm of uni-objective, where the objective function is a scalar valued function of a vector. Earlier, we found out JC is a scalar valued function of a vector. Here, I'm going to have to construct a new scalar. So this is a M vector. How do you convert a vector to a scalar? Inner product. We saw yesterday. So I'm going to concoct lambda is a M vector. So what is this L? L is a mapping from Rn cross Rm to R. Are you with me? L as a function takes two inputs. The first input is a n vector. The second input is a m vector. I know the role of x. I still don't know the role of the magic behind lambda, but that's what we are going to uncover. But this is going to be converted into a scalar. So I build the constraint as a part of the objective function. So this is the combined objective function. I have expanded the space from Rn to Rm cross Rm. So this is called the product space. With me? All of you? So what is the algorithm? You solve this problem as an unconstrained problem in both the variables x and lambda. So what do I need to do? I need to compute the gradient of L with respect to x. I need to compute the gradient of L with respect to lambda. I'm going to have to equate both of them to 0. Gradient of L with respect to x will give rise to n equations. Gradient of L with respect to lambda will give rise to m equations. In general, these equations could be nonlinear. In this case, x occurs as quadratic. Are you with me? Lambda occurs as linear. The gradient of a quadratic function is linear. So we will remain within the linear world. and we should be able to solve this linear system easily. All of you? But in principle, this also applies to a case where the constraints, instead of being linear, could be nonlinear. I want to talk about that for a moment before I consider the solution process. So under what condition this problem could be a different problem, a difficult problem? So let me go it here. So I have the state space, I have the observation space, Z. I want this to consider a H, which is a nonlinear function. So Z is equal to H of X. So what is the definition of this? Z is Z1, Z2, Zm. This is equal to H1 of X, H2 of X, Hm of X. So what is H? H is a function from Rn to Rm. The output is a m vector. The input is a n vector. So you can think of H as X. H of X belongs to Rm. All of it me? Where does this situation occurs? We know where the situation linear occurs, right? The morning we talked about that. So let's talk about this question that arises in meteorology oftentimes. I want to find out whether I'm in the El Nino regime or the La Nina regime. La Nina is better for Indian monsoon. El Nino is not as good. And there is a belief that we are transitioning into La Nina, so Indian monsoon may or may not arrive on time, but is likely to be better for the country. That's a prediction, long-range prediction. So how do you determine the El Nino or La Nina phenomenon? I have to compute the average surface temperature of the equatorial Pacific. Equatorial Pacific is more than 10,000 square miles long. You can't go stick a thermometer. So what do? We use the basic laws of physics. Every hard object radiates infrared energy. So we put infrared satellite that measures the energy radiated. The energy radiated, Stefan's law, the energy is equivalent to the energy captured by the satellite is equal to alpha times t to the power of 4. T is expressed in the absolute scale. And what is alpha? Alpha is the property of the surface that is emitting the heat. Physicists have done an excellent job of trying to compute alpha for every material that is there in the world. So I'm talking about saline surface. So saline surface alpha is known. I do know what the energy is received by the satellite. I know alpha. I want to compute T, inverse problem. This is what's called satellite retrieval problem. Satellite temperature retrieval. That's a nonlinear function. All of you? I'm going to give you another example. I am, speaking of another example, in Oklahoma, Kansas, yesterday night was a big tornadic event. Huge. It has been still going on. It started around 2 o'clock in the afternoon in West Texas, in your country.
Long ago.
Long ago. He studied at the University of Texas in Austin. So there was a line from south of Austin all the way up to Minneapolis, 2,500 miles long, firing up into all that thing, moving east forward. My daughter and son, they did not sleep until 2 o'clock, until the storm cleared that. It's a very big event. Okay, so what do? So they have a radar. The radar looks into a cloud system. The radar sends out signals, and they get the reflected energy. From the reflected energy, they have to compute how much rainfall that this cloud system can produce. So they have to calibrate this. reflected energy versus rainfall. They have to get a functional expression for that. This functional expression was invented in Norman, Oklahoma, at the University of Oklahoma, where there is National Severe Storms Lab. That's a little story I'm going to tell you. We all know Second World War happened, right? America did not participate in the Second World War until they were pulled into the war, when Japan bombarded parts of the land in Hawaii. Japanese planes were flying at low height. They were undetected until the explosion took place. So after they took care of that particular event, the military started asking a question, how foolish we were not to be able to detect this tens of planes coming towards us. We couldn't stop them on that track. Where is my place? They did not have devices to be able to detect a moving object. I'm talking about early 40s. That led the Defense Department to start the radar program. One of the famous mathematicians of all time, Norbert Wiener, was in charge of the analysis of algorithms for that particular project. There's a marvelous piece of algorithm that came out at that time that's called signal detection. When you receive a signal, do you see what is the signal part, what is the noise part? And that began in early 40s. Norbert Wiener has a beautiful solution. Of course, in this context, he also derived several different algorithms and ideas. One of the old radars that military used to develop these algorithms using Norbert Wiener's days, when it became old, they donated to the National Severe Storms Lab in Norman, Oklahoma. The researchers in Norman, Oklahoma used that to study the cloud system, and they developed this functional form. So if I know the reflectivity, I can tell you, I can predict how much rain is contained in the cloud system. That is part of the folklore in radar meteorology these days. So the satellite meteorology problem, radar meteorology problem, retrieval of the amount of rain from the reflectivity, retrieval of the sea surface temperature from the energy measured from the satellite. Those are called nonlinear, static, inverse problems. The function HFX is nonlinear. I'm only for simplicity assuming linear, but every method is also applicable to the nonlinear. Of course, nonlinearity brings its own headaches. You have to massage the nonlinearity, but that's a little technical mathematical nuance, but the ideas carry over. All of it, me? That's right. So linear problem, nonlinear problem, Lagrangian problem. So in the case when I'm having this as a HFX, these the derivatives will be nonlinear equations. Are you with me? That's right. Solving nonlinear equations is more difficult than linear equations. I want to walk before I run. That's why I talked about HFX. Are you all with me? So what do we do is not only simple mathematics, but also relevant to retrieval problem. Estimation of temperature, estimation of amount of rain in the cloud, so on and so forth. Are you all with me? Some of you may know, to some of you this may be new. I hope you all got it. Now, let's get into the mathematics of it. Okay, so let's get on with business now. Gradient of L So before I do that, let me simplify the Lagrangian. So what is this? This is equal to x transpose x minus lambda transpose z plus lambda transpose h of x. Sometimes in the analysis, you will also see a constant half here, Why? I'm going to quickly talk about that now. So if I have a function f of x, let us say x squared, I multiply a times the f of x, a greater than 0, that is a of x squared. I have fx plus c. C is a real number. With me? I have a times f of x plus c. So given this, I can convert this like this. I can convert this like this. I can convert this like this. So let's talk about this now. Adding a constant to a function means what? I'm either lifting up or pushing it down. If I add a constant c positive, I'm lifting the function up. Are you all with me? Come on, guys. Nod your head. It's good for your neck, as I told you. That's right. So let's do that for this example. So what is this? 2 times x squared. If you multiply x squared by a number greater than 2, what happens? It becomes sharper. If you multiply x squared by a number less than 1, it becomes broader. The shape of the function changes, but not the location where the minimum occurs. So if you multiply a function by a constant positive, while the function shape changes, the location of the minimum does not. While you add a constant, either pushing it up or down, the location of the minimizer does not change. If you multiply by a constant and add a constant, the minimizer is invariant. So the minimizer of a function is invariant under these 3 transformations. Then why? That means I can multiply a function to be minimized without loss of generality by a constant a without affecting the minimizer. The minimum value of the function may change, but the minimizing location does not change. So I want you to distinguish minimizer versus minimum value. So when you have a quadratic function, when you differentiate a quadratic function, there is an annoying 2-factor, right? If you don't want to bulldoze the 2-factor through algebra, get rid of it at the source, multiply by the half. All of you? So if you see papers, some place they will add a half, some place they won't. It's a matter of taste. Nobody is wrong, so long as you are consistent. So I'm not going to put a half, but you do know why half comes in. Okay, good. Now let's compute the derivative with respect to x. So what is this like? This is like g of x is equal to x transpose ax, where the a is identity. With me? So what is the gradient of g that we saw in the morning? This is equal to 2ax, which is equal to 2x, because a is identity. Therefore, the gradient of this term is 2x. Please understand, gradient is a vector, 2 is a number, x is a vector. Now, the gradient of this with respect to x is 0. The gradient of this, that's a very interesting thing. Again, we have already done this now. So, g of x is equal to lambda transpose hx. Let this be A transpose x, with A transpose is equal to lambda transpose h. That implies A is equal to h transpose lambda. I'm changing the variable. Are you all with me? I have done it once more in the last lecture. And if this is the case, what is the gradient of g? Is A. So that's the law we already learned. I'm applying the law by changing a variable to fit one of the laws I already know to compute this. So what is the gradient of this? It's the transpose of the product, which is equal to h transpose lambda. I'm sorry, h transpose lambda will come here. Plus h transpose lambda. Sorry. Are you all with me? Do you see the reasoning behind it, please? That's very important. Now let's consider this must be equated to 0. That's a necessary condition. That's called first order necessary condition. So in mathematics with respect to optimization, there are a number of interesting factors. Necessary condition, sufficient condition, first order necessary condition, second order necessary condition, necessary and sufficient condition. All of it may, they're all subtly different but related. All of you? That's right. Necessary condition means bare minimum. Sufficient condition is, yeah, how much money do you need to live? If I have 2 lakhs, why, it's very sufficient, cushy life. But what is the minimum you need to be able to get along? Do you see that, please? Necessary and sufficient. Necessary, sufficient, necessary and sufficient. Necessary conditions are tight conditions. Sufficient conditions are loose. It gives you a lot of slack. Necessary and sufficient conditions are the tightest possible condition. You can't move an inch here or there. All of you? I want you to examine, go back to your calculus book, go back to your optimization book. What are the necessary conditions? What are the sufficient conditions? What are the necessary and sufficient conditions? Please learn early. All of you? That's right. Now let's try to compute. Are you all with me now? How I computed this? Oh, you are taking care of that? Oh, good. I want you to know how you get these expressions. When you read a paper, they won't give you any of these details. It can be shown. And it may take 2 hours for you to show. But that's the style of literary writing in mathematics, in sciences. Why? You have to pay the money for the page. They will charge you $80 per page. So you need to make it as compact as possible. Are you with me? So there are reasons why people say it can be shown. It can be shown. In Euler's days, you know what they used to say, the mathematicians used to do? Here's the problem, I have solved it. I want to know if anybody else can solve it. That's how they published their results. They never showed how they did it. They always challenged others. The culture has changed a lot, thank goodness. Even today's paper, we find it difficult to read. But in those days, in the early days of starting point of mathematics, nobody said anything about how they solved it. What is me? This is the problem, I solved it, it's a solution. I'm challenging you whether I can solve it and get the same solution. All of it, me? That's right. That's right. So I want you to be able to see how you get these solutions now. So now that it is done, I'm going to erase and clear the space. Now I want to talk about getting the derivative with respect to lambda. Fortunately, there is only one term with respect to lambda. There are 2 terms with respect to lambda. So I can rewrite this as x transpose x minus lambda transpose z minus h of x. So this is the only term. And what is the rule I apply? G of lambda is equal to A transpose lambda is equal to lambda transpose A, where A is equal to z minus h of x. So if I consider this as a vector A, this becomes lambda transpose A, which is A transpose lambda, is a linear function in lambda. I have already told you how to compute the gradient of a linear function in the last class. So the gradient of G with respect to lambda is A, which is equal to z minus h of x. You all have an aha here? I want to tell you, if you had difficulty, these are the places where you are likely to have difficulty. If you read a paper, they will say the expression for the gradient can be seen to be, and you have to verify. You can't skip that. To verify, you have to do all these things. And that's what I'm trying to help you. You all have an aha here. Please raise your hands. If you have an aha. I'm looking for people who are not raising their hand. I can only take the horse to water, I can't make it drink. You remember the proverb? You can take the horse to water, but you can't make it drink. I can ask you to ask questions. It's up to you to ask a question. All of you? I didn't force you to ask a question, but I'm glad you are doing. Go ahead. What's your question? You remember, I want to find the gradient of this with respect to lambda. This is independent of lambda. This depends on lambda. It's a linear function of lambda. Oh, one by one. Okay, go ahead. Huh? From this equation I got here? From the equation. What's the question there? Oh. Good. She's my proofreader. Thank you. Thank you. Thank you. So you are not a question. That's good. I missed my sign. Sure. Thank you. Any other observation, question? Good. So what is this? This is z minus h of x. That must be 0. Look at the genius of Lagrange. Solving the second gradient is equivalent to satisfying the constraint. You all have an aha here? This must be an aha moment. I am trying to build the constraint into the gradient equation, and vanishing the gradient is a necessary condition for the minimum. How beautifully done. It's one of the gems in optimization theory. Are you all with me? Come on, guys. Newton was responsible for conditions for maximum minima. Newton and Leibniz is the German, Newton in Englishman. At that time, they simultaneously developed the univariate calculus. In Newton's time, conditions for maxima minima have been known. Lagrange took up the constraint optimization. So it's a fundamental and an enduring principle of Lagrangian multiplier. So I have two sets of equations. This is linear in lambda, linear in x. This is the original equation. I have to solve them simultaneously. Because I'm going to have to solve them simultaneously, my constraint is already built into the system. That's the beauty of it. How many of you have an aha here? Come on, guys. Come on, guys. This must be an exciting moment in learning process of optimization. All of you? I don't want to belabor the issue too much, but you know what I'm talking about. So what does this imply? H transpose lambda must be equal to 1/2 of that must be equal to x. Or I'm sorry, I'm not solving the equation correctly. So this is this. So x must be equal to minus 1/2 of h transpose lambda. With me? Z is equal to this. Substitute this in here. Z is equal to h of x. X is equal to this. That's equal to 1/2 of h transpose lambda. Therefore, I got h transpose lambda must be equal to 2z so lambda is, z is known, h is known, h transpose is known. I know everything, lambda is not known. What is that? That's a linear equation. And let's also find out what is h transpose. H transpose. This is m by n. This is n by m. So the whole thing belongs to m by m. The lambda is m by m. Z is m by m. This is the m set of linear simultaneous equations. So assuming that h transpose is non-singular, now I want you to think for a moment. In the previous case, what did I got? I got h transpose h. Here I am getting h transpose. So given h transpose h. So this is a n by n matrix. This is a m by n matrix. When m is greater than n, this is smaller. When m is less than n, this is smaller. Given a rectangular matrix, I'm creating two square matrices. These two square matrices are called Gramian of H. Graham is a mathematician. Are you with me? Graham-Schmidt orthogonalization. You may have heard of the same Gramian. So given a rectangular matrix, I can create two square matrices. Both of them are symmetric. If H is full rank, both of them will be positive definite. We already argued that this morning. Are you with me, please? How many of you are with me? If H is a full rank, in this case, the rank of H will be n. If H is a full rank, the rank of H will be m. So in this case, H transpose H is symmetric and positive definite. In this case, H transpose is symmetric and positive definite. All I need is rank of H is equal to minimum of m n. So if I assume the rank of H is full, in this case the rank is m, H transpose is non-singular, it inverse exists. So I can write the solution to this to be lambda is equal to 2 times H transpose inverse Z. What's that? Where is the minus sign coming from? The x, yeah, minus. That should be a minus here. That could be a minus there. That's right. You put the minus sign. Yeah. What's that?
In gradient of x of L should be 2x minus x transpose N.
You are talking about this?
Yeah.
To the 2x?
Minus.
This is, thank you. Then there is no minus here. Right? Sorry, you're allowed to make mistakes, but you should know how to correct it. Thank you. But thank you, I stand corrected. Thank you. These are all my proofreaders. Thank you. All of it, me? Okay, good. Now what do? I want to find optimal x. So what is that to do? I need to substitute here. So x is equal to 1/2 of H transpose, 1/2 H transpose, 2 times H transpose inverse Z, 2 gets cancelled. So I get x star. So my least square solution, x star is equal to H transpose inverse Z. And my lambda star is this. All of you? So I have solved for the optimal solution. Now I'm going to compare and contrast the overdeterminant with the underdeterminant. All of you? Everybody please. Thank you for proofreading. Thank you. Yeah, go ahead. You've been wanting in the side to ask a question. Please go ahead. Go ahead, shoot. I'm older, I'm getting a little weak in my hearing process, so you need to talk a little louder as I do, or use the mic.
Lagrangian with respect to x, the del x.
What's that?
The del x of L, that is 2x minus.
Where are we now? Here?
With respect to x, derivative with respect
This is Z minus H of x?
previous.
This one?
2x minus lambda transpose H.
2x minus. No. Please understand. You remember that's what we did here. I know exactly what you're asking now. Let's look at this now. So what is the term that I'm using? Lambda transpose H of x. I want to compute the gradient with respect to that. With me? Hello? Nod your head. I want your approval. So what is this? This is lambda transpose X, lambda transpose A. This is, what am I? I'm missing lambda transpose H of X. So lambda transpose, I'm trying to do with the X, right? I'm sorry. This is, I want to do A transpose X, that's correct. So I want A transpose to be equal to lambda transpose H. So if I define A transpose to be this, now do you think this becomes this? Hello, nod your head one way or the other. That's right. This is a linear function of X. And what is the gradient of this? This is A. But what, if A transpose, this is what is A, the transpose of that. So that is equal to lambda transpose H transpose, which is equal to H transpose lambda. Are you with me? That's right. Now you know what are the troubled spots. That's what I'm trying to smooth it out. Tomorrow afternoon, we have an hour to talk about some of these things. So please bring your questions. Things you wanted to ask, you didn't ask. Please go ahead, add anything you want to. Of course.
Maybe it will be very useful if you can do it once in your life at least, actually multiple times probably, in component form.
Yeah.
Write everything in components.
Yeah, exactly.
X is a vector, x1, x2, xn. The derivative, the gradient with respect to x is basically a co-vector, but vector, which has components, which is del xi, del by del xi of whatever is inside. What are each of the components? Write it once.
We did this morning. We did this morning.
Oh, you did this?
But I did this morning, but your suggestion for each of you to do once in your life, that's the important thing. Hey, he's a professor.
But then I said multiple times as well.
Of course. You have to do many times in your life. He and I have been in the area for so long, including Govind too, still continue to do it. It's a struggle every day. So if you have struggled, you are in good company.
If you don't get it wrong 5 times, then you have
Exactly. Exactly. Are you all with me? So what is the English saying? The devil is in the detail. That's a proverb. The devil is in the detail. You got to go through every place to find the devil. Are you all with me? Good. Now I'm going to compare the overdetermined with the underdetermined. Summary. How much time do we have? Half an hour? Good. Very good. Thank you. But before I go there, any other question? I'm glad you asked that question. Some of you may be sitting on your question. I don't know what else I should do to perk you up to ask questions. I know the student psychology. If the teacher does not let you ask the question, you always say, gosh, he's very harsh, he doesn't take any question. But if the teacher says, ask any question, nobody asks any question. Are you with me? Of course, student life, you want to have the cake and eat it too. You want to have it every week. But you are not students, you are all researchers, right? You should have gone out of that BS mode. You are a PhD mode. You are an individual researcher. You are seeking the truth. So no question should be a bar. No bar for any question. Are you all with me? Well, you want to give her the... I'm sorry, the problem is not you. The problem is my hearing. My age has led me to lose some hearing. I'm sorry. You don't have to stand up. You can sit down and talk. Is that on? Yeah.
Dimension of H is m cross n. So H transpose, it should be like m cross m, right?
Yes, that's
Just
right.
say
That's
there.
right. That's what he said. Here is case m cross n. This is m cross n.
So H transpose, because H is
in
m
one
cross
way,
n.
in one formulation, I need this matrix, and another formulation, I need this matrix.
Yeah, I'm asking about the order. Like,
Okay.
isn't it should
So, I
Yeah.
have switched it. I'm sorry. Yeah, H transpose H, this is n by m. Sorry,
Yeah.
this is m by m.
So then the rank is coming minimum of m and n.
That's right. That's right. So when m is less than n, this is the full rank.
Yeah.
When n is less than n, that's the full rank.
This
That's
is the full.
adaptive. That's right.
Okay.
The mistake was mine. I simply put the wrong sentence. Thank
Okay,
you.
sir. Thank you.
Thank you. Sure, sure, sure. Any other question? Please understand, we are killing all birds in one stroke. I'm now trying, I have combined two presentations, one for the overdetermined, another underdetermined, and I'm going to compare the two, if there are no other questions. But please feel free to ask a question. So Z is equal to H of X. In music, if you are learning piano, what is the first lesson? Twinkle, twinkle, little star. Are you with me? If you cannot play Twinkle, little star after 4 classes, the teacher will tell your mother, I believe this person is made for violin, not for piano, right? Are you with me? I can't play. I love music, but I can't sing, fortunately. So certain people are cut for certain things. So for every problem, there is what's called a model problem. In mathematics and applied mathematics, we always talk about a model problem. So what is the model problem for learning piano? Your ability to play Twinkle, Twinkle, Little Star. If you can play Twinkle, Twinkle, Little Star in all of its variation, then the piano teacher will tell, please, this person, your son or daughter has a lot of promise. You should continue giving them lessons. Are you with me? So what is the idea here? You should be able to solve a good model problem in your area absolutely thoroughly, just like he said, in all its parts. So for the static deterministic data assimilation problem, this is the Twinkle, Twinkle, Little Star model problem. For minimization, what is the model problem? Quadratic minimization. Are you with me? If you can't solve that, don't worry about any other problem. You have to walk before you run. All of you? That's the idea here. So, m greater than n. This is a summary. M greater than n. M less than n. Z is equal to h of x. My x star is equal to h transpose h inverse h transpose z. We saw in the morning. Now we are seeing x star is equal to, I don't want to make a mistake, which is h transpose transpose inverse z. This was obtained from this equation in the parlance of applied mathematics is called normal equation. And this method is called method of normal equation. So method of normal equation for solving overdetermined least square problems. In here, how do I solve this problem? You solve this problem in 2 steps. The first step, you solve h transpose y is equal to z, and then compute x star is equal to h transpose y. Yeah, I have to compute this, so I'm going to call this y. So I have to solve this linear system for y, much like I have to solve this linear system for x. Solving this linear system are essentially the same problem. Why? Both are symmetric positive definite matrices. What are the methods that are used? Cholesky decomposition, QR decomposition. Are you with me? Singular value decomposition. You can also use iterative method like Jacobi method, Gauss-Seidel method, over-relaxation method. Of course, you could have optimized this using sequential optimization, gradient method, conjugate gradient method, quasi-Newton method. Are you with me, please? So if you want to go through all the details, it will probably take 3 full months, working 3-4 hours a day, every day. Are you with me? I also want to remind you, why do you come to these short courses? Just to know what you didn't know, and what is the path you need to pursue to know what you want to know. You are not going to know everything, but you know every path. Are you with me? If somebody can show you the path, you must be able to walk. That's the reason you come to short courses such as this. All of it, me? So this is again a normal equation. So there is a lot of literature in solving these equations, both in direct methods, iterative methods, optimization methods. All of you? So this is the Gramian, this is the Gramian. Under full rank, this is symmetric positive definite, that is symmetric positive definite. So in MATLAB, I need only one program. So Cholesky decomposition will solve both the systems. QR decomposition I can use. SVD I can use. All of it may place? That's right. There are lots of nuances. I'm not going to get into all of that right now. But I want to get into some other related aspects of this. Are you all with me now? Least squares theory is very deep, very broad. You can have a 1 semester course on that. Any question, or somebody ask something? Okay. So when AX is equal to B, we say X is equal to A inverse B. So X is the inverse of that. When Z is equal to H of X, when H of X is equal to Z, I say X star is equal to H transpose, H inverse, H transpose Z. So this I'm going to write as H plus Z, where this is called the generalized inverse of H. Does it look like this? X is equal to A inverse H. If Z is equal to this, X star, or I will simply say X, I don't want to have star. X is equal to H transpose Z. So if this is A inverse, this also plays the role of inverse, but the inverse of a rectangular matrix is not defined. There's a group of mathematicians in the 30s, they worked very hard to be able to define the inverses of rectangular matrices. That's called a generalized inverse. The mathematician who worked on this, two mathematicians, Moore and Penrose. So this is called the Moore-Penrose inverse. Are you with me? Hey, that's what mathematics is all about. Mathematics is continuous generalization. Are you with me? That's right. This ability to constantly being able to generalize by introducing newer ideas. That's what enriches mathematics. That's what mathematical pursuits are all about. So comparing different systems we talked about. If it holds here, can it hold here? If I have this result, how can I generalize this? That's what mathematics grows. The problems in mathematics are created that way. All of you? That's right. So Moore-Penrose inverse, properties of Moore-Penrose inverse. In our book, we talk about, in chapter 5, lots of properties of Moore-Penrose inverse. I just don't want to get into that direction right now. But there is a beautiful graphical interpretation for the least square solution. That's what I'm going to talk about next. So let us try to simplify the problem. Z is equal to H of X. So this is a m by 1 vector. This is a m by 1 vector, that's X. So this m vector H is a vector in Rm. All of you? Hey, it has a direction. I just happen to put it horizontally. Why? Yeah, I need to put it somewhere. So I can put it horizontally. Z is another vector. So Z belongs to Rm. My H belongs to Rm. The angle between the two is not 0. You have learned a theorem when you are in 8th grade, when you do two-dimensional geometry. What is the basic theorem? If there is a line, if there is a point not on the line, the shortest distance between the point and the line is the length of the perpendicular from the point to the line. Nobody proved it for you. They told you. We believed all the things because they are true. We are taught the basic Euclidean geometry, the two-dimensional geometry, when you first do geometry in the 8th grade. If you didn't do geometry by 8th grade, it's too late already, right? So what are the things we learned? Parallel lines never meet. Two non-parallel lines always meet in a line. 3 points are either collinear or form a triangle. The sum of the two sides of a triangle is always greater than the third. The sum of the angle in a triangle must be equal to 180 degrees. If a parallel line, if you cut, the alternate angles are same. There are tons of facts that we have learned. So what is one of the important facts that's related to least squares theory? Is this, if there's a line and a point not on the line, the shortest distance from the line to the point is the length of the perpendicular from the point to the line. What is the key word? Shortest. In the 8th grade, you didn't care for optimization, but that's an optimal solution. Are you with me, please? How many of you remember that? That's right. If you have brother or sister at home, grab the geometry book and read overnight. It's very revealing. It's a long time before we did geometry. We have probably forgotten. I think it's a good dose of geometry to read the 8th grade geometry book. Please do. I'm not kidding. You will come out as a better person in terms of basic understanding of simple things explained in a beautiful way. So this is Z, this is this. So this is the point not on the line, length of the perpendicular. This is 90 degrees. This is Z hat. I want to be able to compute Z hat in terms of H and Z. There is a very beautiful illustration for this. Suppose I shine lights in a direction perpendicular to the direction of H. The Z is going to cast a shadow. The shadow of Z along H, when light is shown perpendicular to the direction of H, is Z hat. Are all of it with me? So the whole question is given Z and H, how do I find Z hat? This is the error E. This is equal to Z minus Z hat. And Z hat is a vector along H. Any vector along H can be expressed as a constant times H. So Z hat must be equal to H times X. X is a scalar. Are you with me, please? How many have heard me? That's right. So this must be equal to Z minus H of X. Does he look like our old friend Error? Come on, guys. I don't see anybody smiling. This is a smiling moment, aha moment. I got the same expression for the error from a simple two-dimensional geometry they learned in 8th grade. Now, what is that I need to show? I need to show this E is perpendicular to this. E is this. Perpendicularity in analytical geometry, how do you test? The inner product must be 0. We saw last class. Geometry, analytical geometry. Everybody please. So how do I express that? H transpose Z minus H of X must be 0. H is this direction. This is the direction perpendicular to that. The inner product must be 0. You have an aha? Aha. That's right. So if I simplify this, what do I get? I get H transpose Z is equal to H transpose H times X So what is X? X is equal to H transpose H inverse H transpose Z. That's my solution. All of you, how many of you have an aha? So I could have derived this. There is an implicit optimization. The implicit optimization comes from Euclidean geometry. The optimization being the length, that the distance is the shortest when it is perpendicular. All of you? So what is Z hat? Z hat is a shadow. What is the mathematical expression for shadow? It's called projection. It's called a projection. So Z hat is the projection, is an orthogonal projection of Z along H. And how do I express my orthogonal projection? So Z hat is equal to H of X. And what is the X? X is equal to that. That is equal to H times H transpose H inverse H transpose Z. This I can rewrite as PH of Z, where PH is equal to H transpose H inverse H transpose. That's called a projection matrix. All of you? So how many matrices we have created out of H? H transpose H transpose, the Moore-Penrose inverse, projection matrix. All of you with me? Come on, guys. That's right. There could be two kinds of projection. At 3 o'clock, if you walk in around it, you cast a long shadow. In the morning, 10 o'clock, you cast a long shadow. But when the sun is above you, orthogonal projection. So, outside of midday, the projections are called oblique. So what is an example of an oblique projection? This is H, that is Z hat. If I shine light in this direction, the shadow is this. If I shine light in this direction, the shadow is this. If I shine light in the perpendicular direction, the shadow is this. The angle between the error and the projected direction, if it is 90 degrees, the projection is orthogonal. If it is not 90, it could be obtuse or acute, oblique projection. Oblique projection. When do oblique projection arise? That's a topic for tomorrow morning. That's what's called statistical weighted least squares. So from the deterministic world, I want to transition into statistical world. What is a statistical world? My observations, I assume they are without errors. Now I'm going to recognize that the observations are going to have errors. I'm going to postulate the properties of the errors. Under the postulation of the properties of the errors, I would like you to be able to redo this problem in a statistical context, taking care of the errors in the observation. I won't take this long because we are not the same person we used to be this morning. Are you all with me? I hope I have transformed you. I hope not me. The lectures have transformed you. The topic must have transformed you. That's a Bayesian learning, right? That's right. Posterior. So what's the plan? I'm going to transition to static stochastic problems. Once I finish that, maybe in the second lecture, I'll start with the dynamic problems. Deterministic dynamic problem, then stochastic dynamic problem that will lead to Kalman. I'm not going to delve directly into Kalman. I need to build certain statistical tools that Kalman did. That's what's called linear minimum variance estimation, Bayesian estimation. Are you with me? Those are all the basic building blocks of statistical estimation theory. Once I do the linear minimum variance estimation, the Kalman filter will fall out of the sky. Are you with me? That's a plan. That's a plan. So we are trying to compress a one semester course into a few lectures. But as I told you, this is not a course. This is a short course. It is meant to give directions. Are you with me? I'm not done for the day. We still have 10 more minutes. The boss is not going to let us do that. I'm just kidding. Are you all with me? Good. Now, let us. Here, I assumed H is a one vector. I want to expand this to Z is equal to Hx. This is m by n. This is n by 1. This is m by 1. I want to do the same thing. We can easily do that. I'm going to show you how to do that. You need concepts from geometry, linear algebra. Are you with me? I have already used the notion of linear algebra, analytical geometry. Orthogonality is tested by inner product vanishing the inner product. Good. So let's redo that problem for a larger case of H being a matrix. So here, C is equal to H of X. H does not have one column but many columns. So I am now going to talk about this line to represent the span of H. You remember the span of H? Subspace generated by the n columns of H sitting within the m-dimensional space where m is greater than n. Are you all with me? Come on, guys. I have a three-dimensional space. x1, x2 plane, x2, x3 plane, x1, x3 plane. So in the three-dimensional space, at least I have three planes that relates to the coordinate axis. I can have any plane from any angle. A plane in a three-dimensional space is a two-dimensional subspace. In a four-dimensional space, I can have three-dimensional subspaces, two-dimensional subspaces, one-dimensional subspaces. Each subspace has a generating set of vectors which are linearly independent. If the rank of H is maximum, the columns are linearly independent. So the span of H must be a n-dimensional subspace embedded within the m-dimensional larger space. How many of you are with me? Raise your hand, please. By raising your hand, by nodding your head, it will prevent you from sleeping. Are you with me? That's right. That's right. Okay, so span of H. Now what is Z? Z is a vector in Rn. Now please understand, this is a subspace of Rm. This is a subspace of Rm. So I'm now going to project this. Z hat must be equal to H of X. So what is this? Z hat is a vector. So this must be a matrix. This is m by n. This is n by 1. This is m by 1. And this is the error. The error is equal to Z minus H of X. And what is the criteria? This is the point in the m-dimensional space. This is the n-dimensional subspace of the m-dimensional space. I'm going to project the point in the n-dimensional space to the n-dimensional subspace. All of you, I know you know it. I know you can imagine that. Are you with me? Come on, guys. That's right. That's That's right. So what is that I need to do? I need to show H transpose Z minus H of X must be equal to 0. If it is orthogonal, so if this vector has to be orthogonal to the span of this, means what? It must be orthogonal to every vector in H. Are you with me? Therefore, H transpose this must be 0. So that essentially gives you H transpose Z is equal to H transpose H of X. Now, do you see this is the normal equation? Are you all with me, please? Therefore, X is equal to H transpose H inverse H transpose Z is the X that makes it happen. Therefore, Z hat is equal to H, the linear least square solution, H times H transpose H inverse H transpose Z. So this is equal to PHZ, where PH is this matrix that is called the orthogonal projection matrix. Are you with me? So I could have derived everything based on this. I could have done this morning itself, but I want to see all the beauties. Are you with me? That's right, all the beauties. The notion, this is what's called orthogonality principle. Orthogonality principle, the principle of orthogonal projection. Orthogonality principle and the principle of orthogonality projection is one of the fundamental results in minimization in mathematics. Are you all with me? You all have an aha? Any questions, please? We can talk about the properties of generalized inverse. We can talk about the properties of projection matrices. Are you with me? So the course is endless. There's so much of beauty to uncover. All of you? That's right. What are the fundamental questions that one generally get to ask in linear least square problems? The following. Let me just, I want to pose some questions too for you to think about. So my X least square is equal to H plus Z. You remember that? All of it with me? That's right. So what is the question? Suppose I change one element of the vector Z. How does the solution change? That's what's called sensitivity analysis. After doing the problem, you found out that you made an error in Z. Do you have to redo the whole problem? How does the least square solution change with respect to changes in Z? That's called sensitivity of the least square solution with respect to errors in observation. All of you? Why is this important? You remember in least square fitting, you hear of outliers? What is an outlier? It's something that is not normal. In other words, if you have an observation, so he is an outlier. So what's one standard result in linear algebra? The estimate is very sensitive to outliers. Why the estimate is very sensitive to outliers? I'm trying to fit a straight line. So if without the outlier, my straight line would have been this. With the outlier, the solution may have been this. Because the outlier pulls towards him. All of it me? So what is the least square solution talks about? It talks about minimizing the distance between the line and the point. So in data analysis, we talk about I need to clean the data I can't eat the data as it is given to me. Cleaning the data means what? Looking for outliers. Can you throw the outliers out? No, you can't. You can't throw the baby with the bathwater. So throwing the outliers is equivalent to throwing the baby out with the bathwater. Are you all in my place? So you got to do an analysis to make sure this outlier is because of some errors or is the real signal. So the people who are working in data quality, that job is purely a statistical analysis. There are lots of beautiful statistical techniques that is meant to identify cleaning data. Are you with me? That leads to what is called robust estimation. What is a robust estimation? The estimate doesn't change. The sensitivity of the estimate is much less compared to sensitivity in the observed data. So that's what's called robust least squares. So analyzing the sensitivity, analyzing the impact of outliers, data cleaning methods, understanding the impact of outliers on the estimate, to create robust methods. Robust methods mean I have to desensitize the method with respect to errors in the data. Are you with me? So what is the homework for you? Please go and look at Wikipedia for robust procedures in least squares. There are books written on robust methods. Also, please look into Wikipedia. Anyway, you are not going to the library, right? I'm not sure that culture is going to change too much. I would love for you to go to the library. If not go to the library, at least go to Wikipedia. Are you with me? Robust methods for least squares. Detecting outliers in data. Impact of outliers on least square solution. Computing the sensitivity of the least square estimates with respect to changes in the matrix H. If H changes by a little bit, how much H plus changes? If Z changes sometime, how far X changes? Are you with me? These sensitivities are very important. So you are not done simply because you calculate the least square solution. In a class test or a homework, you are done. But in practice, you are not. There will be a million questions you have to answer before they accept your result. Am I trying to introduce you to other concepts outside of this now? Please pursue some of these lines. I'm going to change the topic to the statistical least squares, oblique projections. With that, we will finish the morning first lecture. Second lecture, I'm going to start with dynamic problems.
Yes, sir.
So
we will continue the discussion tomorrow, 9:30. Remember, those who came late, poster sessions are scheduled tomorrow. So the arrangements has been made outside, just outside the Madhava hall. Please display your posters there. And afternoon, we will have hands-on session. It is divided into two sections. First will be held by Professor Varahan, in which tutorial classes will be taken. And after that, there is a Python data analysis class. Thank you.